feeds. Mm, just a minute. I'll open up one more system in case if it doesn't connects. Okay, everyone. I hope you can hear me. Yes. Right. So, yeah. Okay. Right. As usual, we will have a presentation. At the same time, we will have one uh, onboard Blackboard writing as well. Okay. So, just a minute. Let me take a board. One minute. I just somehow disconnected. The just a minute. E of KTP. Right. So my Blackboard is also ready. Kindly excuse me. It took me for a minute. Okay. So what we do is we'll just quickly recollect what we have done in the last session, and then we'll continue. Okay. Right. So this is what we did last time. The signal conditioning. Okay. And signal conditioning do have a lot of noise. Okay. So due to that noise, we need to work, especially when it comes to quantum computing, we need to work. How should we go about? Okay. Right. So now a motivation I would like to give quickly. Why do we need to get into the signal conditioning in the case of quantum computing? So uh, Phyllis are actually mentioning about quantum coherence. Okay, right? So let me quickly connect in the context of coherence or quantum coherence. Okay, which is very important. If let's say if there is no coherence, means noise is actually causing such coherence. Okay, so first of all, let's understand that part briefly for maybe 5 or 10 minutes. It's worth spending time. Okay, so right, I will just say quantum coherence. Okay, right. So this can be explained from the quantum optics context, but what we'll try to do, we'll try to address it from quantum computing side. Okay, when it comes to say quantum qubit side, which is very much important when it comes to computing, information processing, and quantum hardware. Okay, so what is the first thing comes to our quantum hardware is a quantum bit. Okay, quantum bit, which is in short qubit. So what is this? This is something which stores both 0 and 1 simultaneously. Okay, it's like a memory which stores both 0 and 1 simultaneously. That is what we were told. Okay, how it is done, it's up to us. We choose a different kind of a hardware to realize this kind of a memory. So for example, if I realize such memory using a spin qubits, okay, spin qubits means electrons are nuclei. Okay, these are known to have their own magnetic moment, just like they are like a small bar magnets. So those bar magnets can be aligned as north and south, north upwards, south downwards, or south north. So it is called upspin. Okay, or when it is downwards, it's called downspin. Okay, upspin and downspin. And since these things are quantum in nature, means microscopic in nature, we cannot certainly say both are possible individually. Certainly means at a given time, the system also exists in upspin and downspin. Okay, so in that way, what happens? I can prepare a superposition state of quantum system of, let's say, electron in a ket form, a matrix form, or a vector form. I'll represent for an electron. It will exist in upspin sometime. Also, it exists in downspin sometime. Sometime means when I make a measurement on the system, try to find in which direction it is pointing out. If I make 100 attempts out of 100, I will say alpha square times I'll get upspin, beta square times I'll get downspin. Okay, so this is when it comes to spin electron. Okay, I'm just talking in terms of material based qubit. I can also get a quantum superposition state by taking an actual full atom itself, where atom can be having orbits like this. Let's say one orbit is there, electron is stuck to one of the ground state orbit. Let's say you call that as a 0 and you call it as a 1. The next excited state is a excited state. Okay, here the electron can be in the ground state or it can be excited to excited state. How? I would supply an energy of photon which exactly matches with this transition frequency of energy. Okay, if I supply such photons whose energy is exactly matching with that transition frequency, in that case we expect, I'm not saying certainly, we expect electron to go to the excited state and live there for some time. When I make a measurement, such an action, such an entity or such a process, I would see only certain amount of time electron going to exist in the excited state. Means out of 100 times, if I make such a experiment of incidenting photon, electron would go and live there. Sometimes may not live there sometime, because it's all probabilistic in nature, right? It is no more deterministic in nature because it's quantum. Quantum means such a confusion, ambiguousness is there. Okay, so now this is a qubit for you. And also, if I realize a qubit from energy point of view, like using energy, let's have photons, right? Even using photons also, I can realize a qubit. How? I'll take a qubit. Photon is what? Having some, which is taken from where? Electromagnetic wave. It is a part of EM wave. Okay, electromagnetic wave, let's say electromagnetic wave is traveling, means the energy is traveling. In that energy, a part, like it's like a dust particle, same photon is a speck of energy, small speck of energy. So that is traveling. If I pick that small energy entity, that may have the electromagnetic wave energy, like polarization into particular direction. It can be vertical polarization or horizontal polarization. Okay, that is what polarization for an electromagnetic wave we call. So that polarization can be what? It can be horizontal or it can be vertical. Okay, so since the photon is also microscopic in nature, tiny in nature, okay, energy wise very small entity in nature, what we do, we'll have to keep it into superposition state and realize a qubit out of it. Okay, you see, whether I realize a qubit out of material like an electron, whether it's in spin form or it is in excitation or de-excitation form, okay, right, or photon in its polarization vertical or horizontal, in all the cases it is very very important to have both the states existing simultaneously. That is very important for me. Let's say one of the state never exists, means I am into certainty, means classical form, there is no quantumness anymore. Why classical is certain? If I keep something on a table, it is going to remain on a table forever. It is not going to be displaced unless somebody comes and disturbs it. That is the inertia of rest for something which is on the table. Okay, so you see, having both the states is very very important. Okay, so in order to have a qubit without being disturbed, I need both the states to exist. Okay, so now let's come back to the concept of coherence. Okay, now we will take the superposition state realized out of an electron, whether it is an excited or a ground state, that as an example, and we'll try to understand the coherence part. Okay, so what we'll do, let's say I'll have a two-level atomic system. Okay, what did I do? I just taken a snapshot of that entire atomic part and just drawn as two horizontal lines. Now let's say electron is in the ground state for time being. When I supply bunch of photons, which is having exactly energy wise equal to transition frequency, in that case, what happens? This electron has a chance to absorb that energy and go on to stay in the excited state. For how long? Usually from 0 to 1 microsecond. Okay, roughly saying on an average 1 microsecond. Okay, so the electron would go and live there. After 1 microsecond, probably it comes down, and whatever energy it has absorbed, that energy is emitted out as a same photon. If I leave the system on its own to de-excite after 1 microsecond, that would be spontaneous emission. Okay, means I let the system to deactivate or de-excite on its own. Okay, atomic system. Now let's say I can force before 1 microsecond. If the system is in on the excited, electron is on the excited state, it is waiting for 1 microsecond to cross. Even before that, I can force the system to just de-excite. What I'm saying, let's say one of the photon is absorbed, electron is in the excited state. Now what do? I want to pull it down before 1 microsecond. What I will do, I will not do anything. I just send one more photon just before 1 microsecond. You know what happens here? This photon just see, this photon is no more required here because there is no ground state electron. So this photon is just no business. It has to travel out. But you know, in general, in reality, what happens? While going, this photon somehow disturbs the nature of the excited electron in such a way this electron is forced to come down and emit the photon which is accepted or absorbed in the first place. You know what happens due to this? Due to incident, like an incident photon is coming, which will just go without being disturbed. Only thing, it has triggered a emission from the electron. So the emitted electron, the electron which came down will emit one photon. The old one which is sent by me, that also comes out. So basically I'll get two photons from this process. This is called stimulated emission. Means I had forced the system to emit, means stimulated. Okay. Now you see the difference between previous to the current. This one is previous one electron on its own spontaneously doing, but I had forced this time. Okay. Now there are few things I have to emphasize here. You see, the amount of time the electron spends on the excited state is very, very important factor, which is called excitation lifetime, usually represented by T1. It is also called uh, transverse as a longitudinal time or longitudinal rate or something like that. But you can remember, let's say it's a excitation lifetime. Okay, excitation lifetime of the electron. Now, what I want system to become superposition, system to exist in both the states simultaneously. But when I do this, excite the electron by photon, it goes there and leaves there for 1 microsecond. Okay. If I send one more photon, it is forced down to come down before 1 microsecond. Okay. This is become stimulated emission. Now what I can do is I can just place my incident photons 1 microsecond apart. You know what happens? First, let's say I have ground state electron. I'll send one photon, which will push the electron to the excited state. Okay, it stays there for 1 microsecond. Now what I'll do, exactly after 1 microsecond, I'll place one more photon. Now what happens? Because of that, after 1 microsecond, electron is coming down because no stimulated emission, it is doing on its own spontaneous emission. By the time it comes down, I have one more photon which pushes the electron to go again. Okay. So by the time photon electron is coming down, I'll send one more photon. So basically what I'm doing, it's like a juggling, or let's say somebody is playing in a park with a swing. Okay, you are giving a in synchronization, in sync push you are giving to a swing in a park, you see. By the time it comes to you, you give a push. So it does an oscillation continuously. So basically you are working in sync, in resonance with the a swing in the park. Similarly, what I am doing, I am sending one photon at a time, 1 microsecond apart. So you know what happens because of this? Electrons start from the ground and start going to the excited state and comes back with 1 microsecond apart. It is doing flipping between ground and excited continuously. It is simply equivalent to, let's say you see the fan wings in our ceiling fan or a table fan, wings are rotating if throughout the entire 360 degrees. Likewise, here electron is going down, up and down continuously. Okay. So this is what superposition state for us. Why it is superposition state? Now let's say electron is doing hopping between ground and excited. Now what I'll do, if I make an observation on the such system, sometimes I find the electron in the ground, sometimes I find electron in the excited. Okay. So which is going to become a superposition state for us. Okay. So that is a quantum qubit state for us. You see? So that is very, very essential thing to do a quantum computing or a quantum processing. Okay. So now you see the factors which are very, very important is here I presume the electron to be excited for a lifetime of 1 microsecond and I place my next photon 1 microsecond apart. By any means, you see, by any means, this lifetime of T1, if it is by disturbed, okay, not by me, by the environment, it is possible. So they are so delicate, so small, it can be disturbed. Okay. So because of that, let's say if the T1 get disturbed, it messes with my arrangement of photons, which excites the system to become such superposition. So if the T1 is supposed to be 1 microsecond, but it is become less than 1 microsecond, let's say it becomes 1 nanosecond, you know what happens? it mismatches with my incoming bunch of photons, okay, in that case, what happens? I'll not be able to prepare such a perfect superposition state. Okay, so such a disturbance is caused by environment around. Probably one more qubit is around, probably another nuclei is around, another atom is around, or some temperature is raised in the system. Okay, all sorts of things which we saw last time, all those noises can come into play and disturb this T1 lifetime. Okay, so the decoherence we call is that something which is going out of my coherence, out of my in sync when the environment disturbs the system by disturbing the T1 lifetime, the excitation lifetime. Okay, so since I'm calling T1, there should be something after T1, that's something like T2. What is the T2? Okay, please see now T2 is called longitudinal lifetime. What is a longitudinal lifetime is? I'll tell you what. Now you go back to a simple pendulum experiment. Let's say take a pendulum. You just drag a pendulum to the extreme end and you leave it. So what it does? It makes an oscillation in time. So if you just draw oscillations in time versus oscillations versus time, amplitude versus time, if you do, you see oscillations are there. Okay, up to some time the oscillations are there. Nice sinusoidal harmonic oscillations. After some time, you see oscillations decay, obviously, because I'm not giving any more energy. So the lifetime of oscillations is fixed depending on how much amplitude I'm giving. If I give a large amplitude, it will oscillate for a longer time. Okay, so the time or the duration of oscillations lifetime. Okay, right? So something like that here, our electron does an oscillations between 0 and 1, ground and excited continuously. How long it exists in that superposition state is like how many how long it makes an oscillation, how long this lifetime of being existing both in ground and excited exist. So that is called T1, sorry, T2 lifetime, oscillations lifetime. Okay, that is lifetime of oscillations. Okay, so now you see I had put my T1 perfectly, ensure the system is not disturbed from the T1 perspective, but when it is oscillating, let's say another oscillatory qubit comes, it will disturb. So in that way, what happens? Their lifetimes get disturbed. So that is a decoherence happening from the perspective of T2 side, longitudinal side. So please see the qubit can be disturbed from the T1 side or T2 side. So these two called T1 and T2 decoherence times. Okay, right? Very important when it comes to quantum qubit realization. How these decoherence factors are going affected mainly due to the environment around, mainly due to the temperature around, mainly due to the pressure around. Okay, and all those things we have to capture into the process to do a quantum computing or anything. Okay, so shall we get back to our presentation and then we'll go ahead. Okay, fine. So last time, like I was saying, last time we did discuss about dealing with means the how to deal with such noise. Okay, right? And what kind of noises are all just there? That also we saw. How to quantify them also we saw, right? Okay, so in today's session, we'll again revisit a little bit in a different perspective, those things. Okay, right. So let's continue. So the first slide is about what we discuss. Okay, right. Here you see it. Let me take a notepad of this itself. Okay, right. Okay, the question is why this topic matters for us. Why should I touch this topic when it comes to engineering quantum technologies? Okay, why should I know about signal noise quantification factors. Okay, right? Okay, so right side you see I have a slogan, one of the core challenge it describes. Okay, so what it says is quantum systems don't fail. Remember, they don't fail. They actually they don't fail because they are very complex, but they fail because we cannot measure them cleanly. Means quantum systems by nature so delicate. Okay, it's so delicate we cannot measure them. When we start measuring, it becomes classical. Okay, without pushing the system to become a classical, we need to keep them intact quantum and then measure. So just to know whether it is clean or not, we have to measure, but it's not possible. So that's why people are doing all sorts of new ways, innovative ways to measure the quantum system. They use something called readout technology. Such things they'll use. Okay, right. So here I have for you the quantum systems carry a signals at the level of single photon. What the range, energy range? You see, 10 to the power of minus 23 joules. So small. Okay. Even the quantum information is realized using materials like electron spin or anything. If I had to specify their energy range, which would be what? It is about 10 to the power of minus 23 joules. So small. Okay. And by intuition, if the energy is so small, means energy emitting out of such system is also so small at the same level, and information coming out from that system is also that so small. So our easy, like quick, straightforward temptation is we need to amplify it. Okay, so the amplification is straightforward and straight away necessary. But you know what happens when we try to amplify? We are going to inject the noise into this system. So in this way, we're actually injecting the noise into the signal coming from that system. Okay, and especially the noise in quantum systems is not just inconvenient. Okay, so in classical system we get the noise. Okay, we can disregard it or get rid of it. But in the case of quantum systems, you see, it is coming because of the law of nature. What is that is, we can never ever measure certain things like position and momentum with 100% accuracy. Together we cannot measure them. One of them, if you try to measure a position, you will lose the accuracy in the velocity. Even in real world scenario also, if you see, okay, right, when you don't use a powerful like visual aids like some cameras, slow motion cameras are not doing something. If something is moving very fast, you can't measure its position. If you try to measure its position, velocity you can't measure. Okay, so you see blurred image sometimes, something which is going very fast. So that is due to a inability of ours to measure position and momentum. Momentum means what? Mass into velocity. We can't measure the velocity and momentum as a position exactly what they are at a given instant of time. Okay, so that is coming because of the nature. Nature has put that such constraint. Okay, so the understanding the noise limits is essential when it comes to reading the qubit, when it comes to applying the qubit for some applications like quantum sensing and quantum communication. Okay, so that is why we should have a better understanding on signal to noise ratio when it comes to working with quantum systems. Okay, right? So let me go for that. Yeah, fine. So, okay, right. Now you see here, I have a simple comparison between classical engineering to quantum engineering. Okay. So we will just weigh both the things and say what they are, and we'll have a better understanding here. See, in the case of classical engineering, noise for sure it's an unwanted disturbance, but when it comes to quantum, it is a fundamental property. When it comes to classical engineering, you can amplify the signal freely. We don't bother even disturbance also, noise also gets amplified. We have a ways to eliminate or separate. But when it comes to class quantum engineering, amplifying straight away would also amplify the noise also to very higher values. Okay. So, and separating is not that easy when it comes to noise from a signal in the case of quantum, because there is a standard quantum limit. Okay, so that is Heisenberg uncertainty that imposes that standard quantum limit. Okay, and moreover, last time when we discussed, there is no way I can just remove the disturbance in the system or vibrations in the system even at 0 degrees Kelvin. Okay, even at that point there is a vibration in the system, there is energy in the system that is coming because of 0 point energy, which is what h omega by 2. This much energy is always there in the system irrespective of the temperature. Even if you reduce the temperature to 0 Kelvin, even in that case system is going to have such a disturbance or such energy in the system. With that, things will be very much dynamic. Okay, that is a standard quantum limit for you, right? So in the case of classical system, you can measure and find out whether disturbance is there or whether some issue is there. But when it comes to quantum, you can't do that straight away, because if you try to measure, you are disturbing the system. So there is a way to do that. There should be a innovative way to do that. Okay, so half photon noise is always remain. That's what I said. But in the case of classical, you can reduce this to close to zero. Means you can eliminate the signal. I will show you some plots as we go for that. We can eliminate. Okay, in that way we can have a very good signal to noise ratio. Okay, right? To excellent signal to noise ratio is completely dictated by the existing technology. So you have a better advancements in the this devices, you can have a very good SNR, right? So that is what lock-in amplifier, other things are actually coming in where SNR could be enhanced. But the site like a technology may not assure us a very good SNR in the case of quantum systems. Why? Because whatever advancement you go, you can't reduce the noise below this h omega by 2. The energy of the disturbance cannot be less than this. Okay, so that is what a standard quantum limit. Okay, I hope now you have the the weighing between classical to quantum, why we need to do that. Okay, now as a part of today's session, we'll just see what is the signal to noise ratio. Signal to noise ratio is just a comparison between how much power is there in the signal, how much power is there in the noise. It's just a simple ratio. So people used to describe it in terms of decibels. What is a decibel? Decibel is, for the sake of the people who don't know decibel, which computer science people may not be, but mechanical and electronics people they all know. For them, it's straightforward. But the other people, I'm just telling, SNR in decibel, instead of writing just a simple fraction, we'll just take a log of that fraction, multiply that fraction with the 10. Okay, so what happens in that case? It is represented in terms of logarithmic scale with a base 10, that is a decimal, sorry, with a base 10 multiplied by 10. If I do it, for example, okay, I'll just take a simple example. Let's say a P signal is, say, something like 1000, okay, power. Units is some power, whatever, joules or something. let's say P noise, okay, let's say 1. Okay, so in this case, what happens? SNR would be 10 to the power of 3. Now, in the terms of decibel, what I'll have, which is equal to 10 logarithmic scale base 10. 1000 by 1 is just 1000. 1000 I can represent as 10 to the power of 3. Okay, so log of 10 cube is equivalent to what? I can bring the exponent to the left by saying, okay, let me read, okay, maybe I can show you here. Okay, simple SNR is P signal to the P noise. Okay, what we have here is 1000, let's say joules. Let's say noise is just a 1 joule, so which is just 10 to the power of 3. Now SNR in decibel is 10 multiplied by log with the base 10, okay, right? SNR, which is 10 into log 10, 10 to the power of 3, okay. So using just a formula in log, in that case, exponent can come in multiplied to the log. So this would be log 10, 10, okay. So if the base is 10, if you take 10, which is this part is, sorry, this part is just equivalent to 1. Okay, what do I have? SNR in decibel is equal to 30. So I'll just say 30 decibel. Okay, so let's get back to our presentation here. That is what we have. So if my signal power is 1000, okay, and if my, yeah, if I have the noise power is simply 1, so if my SNR expressed in decibels, 30 decibels, we'll say very, very real, reliable signal it is. Means noise is just 1 part in 1000. Okay. If by any means it is becomes 10 decibels, means what? It is reduced by 1/3. Okay. Reduced by 1/3 means instead of being 30 decibel, it is reduced to 1/3. Means what? What is the P signal here? P signal is just 10, right? And what is the P noise? Sorry, 1000. What is the P noise? P noise would be what? 100. Okay, in this case, what would be the ratio? Ratio would be, okay, SNR in this case would be 10 into, okay, log 10, 1000 by 100. Okay, what do I left with? Just simply 10. Log 10 of 10 is 1, so I'll have 10 decibels SNR. So here, out of in my signal 1000 joules, 100 joules is noise. Okay, I'll specifically show the specific noises. So here is okay. 10 parts in a signal, sorry, 10th part in a signal is noise. Okay, reasonable. We can say acceptable. Okay, right? So Satya Priyaji is saying 30. Yeah, 30 is in the previous case. This case it is 10. Okay, right? Yeah. Yeah. Now, let's say if the signal and the power both are equal, so signal and the noise both are equal in power, in that case, what happens? SNR becomes just 1. The ratio becomes 1. You see, signal is 1000, noise is 1 minute, 1 minute. Okay, the noise is 1000. The ratio is 1. You know what happens in that case? What will be the SNR? SNR is 10 log 10 1. Okay, log 1 is what? 0. This quantity is 0. So SNR in decibels in this case is 0. Okay, so you're saying if the noise and signal are the same power, we are losing, we don't see anything, we might always make a mistake. Okay, right? That is what the 0 decibels are expressed in the case of, in terms of decibels, the signal strength. Okay, so please remember, such cases are unusable, not at all reliable when it comes to any process, signal processing or anything, even in the classical communication, which may be the case in the case of quantum, because the signal strength, like I showed you last time, is about 10 to the power of minus 23 joules. Okay, right? So I just expressed the energy in my PPT here in terms of joules, and power is a part of signal power. Okay, energy is a part of the power, so you have to modify that. Okay, okay, joule second is the power. Okay, right. So now maybe if you want, I can do that. Right. Okay, so now get back to the PPT. So the key insight here is amplification increases both signal and the noise. So the real challenging is preserving SNR. What I am saying is, by equal ratio, if it increases, fine, we are through, because it is the ratio of both things. So if the signal strength increases by 10 times, noise also increases by 10 times, fine, because it gets cancelled, our SNR is intact, and we can rely and sit in the range of reliable signal range or acceptable signal range. Sometimes, it becomes improper. Sometimes noise is amplified improperly, more than signal amplification. In that case, my SNR is going to be disturbed, which is not at the higher level. Okay, if it gets lower level, then I have to struggle in the processing, which is very much possible in the case of quantum computing, because it is working at the level of microscopic range. Okay, fine. So there is a visualization, like I was telling you. You see here, SNR visual comparison. If I happen to have, let's say, noise signals, my SNR is in 30 decibel range. Means SNR is just 10 to the power of 3 in the decibel. SNR conventionally represented is just 1000 by 1. In that case, you know what I say, if my signal is something like this, in that disturbance is something like this, very, very small. Okay, so fine, I can somehow streamline that, eliminate that such disturbance. Okay, but if my signal strength is so small, it is like this. Let me take a different color so that you people can see. The signal is something like that, but your disturbance is so much. You see, unless if I don't concentrate, I will not able to figure out whether it is a harmonic sinusoidal signal or not. You see this, the amplitude is so small. You see, the amplitude is very, very small. When it comes to noise, amplitude is large. Okay, how large? Nearly 5 to 6 times larger than the signal strength. So in this case, we say very low SNR. Okay, and in fact, the system is noise dominant. Okay, right? So high SNR systems extract more information from the same measurement. Okay, which is critical in quantum computing when it comes to qubit readout. Okay, when I have to read the system quantum superposition state, this is goes and makes a big impact. Okay, fine. Little bit more visualization for a better understanding. You see, okay, I pick for the case of high and low SNR cases. Okay, right? Let's say my signal is, let's say, some rectangular waveform. Noise is, let's say, 10%, like a 10% of the strength wise, signal wise. If I am adding it, what kind of a signal I'll get? I'll be getting signal like this. Okay. If I'm amplifying, the noise becomes amplified to such a level, and signal becomes such a level. And what would be my overall signal? It's fine, reasonable. I can figure out it is a nice rectangular waveform. But if my signal is amplified to certain level, and at the same time noise was not there earlier when I do amplification, so amplification is went on to add a lot of noise and bring the noise in the same level of the signal level. In that case, what happens? You see, the signal plus noise, the overall output from a system, you see, you can't figure out if it is a waveform or not, rectangular waveform or not. Okay, so that is what high SNR to low SNR signal output would be. Okay, right? So right earlier we had a signal plus noise in a smaller SNR. Okay, and in that case, you know what I can do? You can simply remove the noise. There are ways to remove the noise and extract the actual signal. You can isolate the noise and get the actual signal. Okay, fine. And here we have something for you. Original signal with the multiple frequency components if I have. Okay, right? Here I have showed you one single frequency, but let's say my signal has multiple frequencies. Okay, right? And if there are multiple frequencies are nice sinusoidal with different fixed values, if you just take a frequency spectrum of this one, okay, let me take a different red color. Okay, frequency spectrum of this one, if take, right, frequency versus the strength, amplitude, if you draw, you get nice peaks. Okay, single peaks corresponding to each frequency. Okay, it's fine, very good. Many frequencies are there, many signals are there, just like our digital communication. Okay, many channels are there, digital telecommunication, all those carry the different information. Okay, if those multiple frequencies are few are there, fine. Among them, many of them are exist at a very low energy range, and if there are many are there, it becomes a noise for you. In this case, if you just take a frequency spectrum, you know what happens? The frequency, instead of having a single peaks, it is going to have a continuous, like a hill, some kind of a something like that. Okay, so there will be single peaks very close, but you see, apart from that, at lower level energy, lot of complete, like, filled out peaks are there. Okay, those are corresponding to many frequencies due to this noise. Okay, so this is a frequency spectrum we have. From there we can figure out whether the noise is there in my signal. You see, noise is there, it's a very low, few peaks. If the noise is there too much, we'll have like the frequency spectrum at a very lower energy level. There is a we have curves with the filled out curves. Okay, so in this way we can also measure and quantify how good is my signal coming from a device, whether it's a quantum device or even classical device. Okay, so high SNR extracts more information from the same measurement. It's critical in quantum computing. Okay, fine. Now, okay, so in reality, when you try to do amplification, you are adding the noise. Okay, so which is a reality, amplification reality, right? And so we are working at the temperatures more than 0 Kelvin. Okay, right? So in that case, the temperature noise also comes in. We discussed this last time. And also there is something called short noise. What is the short noise? We are not working with the ideal individual systems. When you put them together, they are no more become same type of system. It's like a discreteness, non-inequality, sorry, non-uniqueness among the systems. Everything when they're separate, they are ideal. They are not deviate from a requirement. When you put them all together, they start interacting. In that case, some of them just deviate from the actual requirement what I need in the first place. So that is actually the called short noise. Okay, right? So to deal such thing in physics, there is something called the Poisson statistics are there. Okay, Poisson statistics, Fermi-Dirac statistics, Bose-Einstein statistics. Likewise, there are three different kind of statistical methods used to study the systems. Okay, so which system to be used also will be decided by what kind of systems they are. For example, electrons. Okay, they can be studied using Poisson statistics or Fermi-Dirac statistics. Okay, when it comes to photon, Bose-Einstein statistics they'll use. Okay, right. So this is I think it's a part of physics. You'll get to see them when you are going and using quantum sensing in depth, how to use the quantum sensors, how to retrieve the information from quantum sensors, whether the information is correct or not, how to deal that is using this statistical mechanics. Okay, right, right. So finally, the quantum noise. It exists even at absolute zero due to Heisenberg uncertainty. We already discussed that, which is exists half of photon range, the 0 point energy. Okay, there is no way I can't disregard this 0 point energy. That is a quantum. So you have to live with it. And you say noise is always due to imperfections. Sometimes it is even due to very structure of the reality itself. The first two cases, you see it? Okay, it can be imperfection in the system because surrounding temperature, if I cool it to millikelvin, sometimes the cooling mechanism doesn't work, that induces the noise. Okay, fine. So the short noise. So I prepared individually all the ideal system and they put together, they're no more ideal. They interact and they just deviate. So that is the imperfection in the system. But the quantum noise, you cannot say imperfection in the system because you cannot prepare it ideally at all in a perfect way because always this noise h omega by 2 is there in the system. Okay, right? So when you amplify, you have to keep that into context. Okay, so specifically what thermal noise can do. Okay, for example, if I have a temperature of the system is some TA, it is emitting a signal with a bandwidth BA. So what is the power of that system? The power of that signal is simply a Boltzmann constant multiplied by temperature of the system and in what bandwidth it is emitting. So that is the power of the system. Okay. Now you see, if the temperature of the system is, let's say, 1000 degrees Kelvin, okay, right? So for example, if I just take a resistance with a 10,000 ohms, if you measure the current going through it or a power going through it, okay, if the temperature is so high, you know what happens? Okay, you see a lot of disturbance. Okay, and for that disturbance, this is a temporal signal. To take a spectrum of it, what I was showing you earlier, or spectrum with respect to frequency, okay, angular frequency I draw or conventional frequency, which is a f if you take, you see, instead of getting single peaks, you're getting many peaks like that. So if you amplify them, what you see is individual peaks, many individual peaks. Okay, so such many frequencies are there in the signal. They're actually coming because of the noise. It's like in your actual signal, lot of noise signals are there. You can't search what is the right signal from this bunch of noisy signals. Noises are there. Okay, fine. Next, if the temperature rises, such disturbances rises. Okay, and short noise. I was telling you earlier, systems are no more individual; they are become clubbed together. In that case, let's say electrons are there. In the case of current carrying wire, with some current, it is carrying with some bandwidth. Okay, in that case, if I try to measure, right, the average of I square. Okay, this is how the short noise is being measured. Okay, in that case, you say if you draw amplitude of the signal with respect to time, you see a lot of noise. So here, whether the signal is like this or I don't know that, we have to eliminate the noise and then we have to get it. So the short noise waveform would look like this. There is a way we have to find out to remove that short noise. Okay. Now coming back to quantum noise. What is this quantum noise? Quantum noise means if the quantum system is there, it's like a particle, like electron, like a photon, located at some point or moving from one point to other point. So there, usually we represent any dynamical system by its position and momentum velocity. If you multiply the velocity with the mass, it becomes linear momentum P. Okay? Heisenberg uncertainty says delta x into delta P is always greater than Planck's constant by 2. Means you cannot measure position and velocity perfectly. Means if I draw delta x, let's say, okay, if I have x-axis, along the x-axis I'll represent a position, along the y-axis if I represent a momentum. Okay, all right. So instead of position I'll say delta x, delta p. What is this now is how much error I make, how much error I make in position measurement, how much error I make in momentum measurement. So at any given point, you can balance both of them and make it equal. Okay? What I mean is the like error-wise same ratio, delta x and delta p, same ratio very close, so that delta x and delta p add same contribution for the error, overall contribution. Okay? Right? So sometimes, you know what happens? I presume I don't want accuracy in one of them. I don't want accuracy in, let's say, position. I want accuracy in velocity. For example, in the case of a cricketer bowling a ball, a fast bowler. So, okay, Prahalad Rao Abibi is asking, is I and capital I both are same? No, they are different, right? So when it comes to signal measurement, I small I square is being used, which is a fraction, sorry, which is a formula, this formula, right? This formula. Okay, so this angle brackets are used to say mean value. Okay, I measure this fraction of q into I into b several times, and that I represent as a short noise. It's called a Schottky noise. Okay, fine. Now coming back to discussing about the quantum errors, right? I don't want accuracy in one of them. For example, a cricketer is bowling. It's a classical macroscopic system. We can use it as an analogy to understand what we are doing at a quantum. Okay. So here it's a, if I don't want the position of the ball accurately measured at a given point, what I need to know what is the speed with the cricketer is bowling. A bowler is bowling. So there I say I don't mind having the error in the position, whatever I want, whatever it can, but I want accurate velocity. Okay. So in that case, I'll reduce my P to very small values and let the delta X go high value. You know why? Both of them come hand in hand because their product is always greater than Planck's constant by 2, where H is Planck's constant, H cut is H by 2 pi, H cut by 2 means H by 4 pi. So what I'm doing here, I am reducing the error in the P, velocity, angular, like linear momentum part. Okay, what I'm doing, I just compress the system at the vertical scale. You know what happens there? I just have 1 minute. Okay, like that. So what is here now? New delta P, let's say delta P prime, much larger than actual delta P. New delta X is much smaller than, sorry, much larger than old delta X. See here, delta P prime is much larger than delta P. Delta X prime is much smaller, much, I'm sorry. Okay, I have to make correction here. Yes, this is delta X is much taller. This process, you see, it's like a nice ball is there, elastic ball. You compress. You are compressing in the vertical level. You are squeezing it to some kind of ellipsoid. Like a regular football is there, you compress it, you make American football. Okay, a rugby ball, right? So this is called a squeezing process of squeeze, and you obtain a state called squeeze state. Okay, so this is very much important when it comes to a photonic quantum computing where current states are there. Okay, and we will get squeeze state out of it. Okay, current states, squeeze states, and there is something else also there, Fock states, F-O-C-K, Fock states. Those things are again will come in the case of quantum sensing and so on. When it comes to noise, what we should know here is we can reduce the noise in one of the coordinate. Any system, usually we meant to represent the system by using what? Position, momentum, that is velocity in given time. I'd say temperature of the system, pressure around the system, okay, and what is the overall volume of the system. Likewise, there are so many parameters to represent a given system. Okay, right? For a given system is represented by usually the position and momentum. One of them, I just compromise. I don't mind any error in it, but I want more accuracy in one of the case. So P, I want more. I'll reduce the error in it and let the error can go any amount in the case of other unit. So here X and P are called quadratures. Okay, they complement it. They come hand in hand with each other like a two players. Okay, so they're called quadratures. Very important in the case of computing, quantum computing. So we will say a lot when it comes to sensing. Okay, see here, I want more accuracy in the case of position. What we can do? We compress at the position level the error and increase the error. Let the error can go in the momentum side, but I want more specific location. Okay, so that is what quantum fluctuations can do. Even vacuum in the sense zero, at 0 point temperature. Okay, at that point we have fluctuations at the energy scale of h omega by 2. At that case it's called vacuum, nothing else is there around the system, vacuum. Okay, so those fluctuations case we can do such squeezing. Okay, right. Now SNR we just saw. Okay, another way of quantifying the system signal is a noise figure. We saw last time also this one. So here we have a device. Okay, we send some information into the signal and into the device. It processes it and it gives out. let's say a device which removes the noise from the signal. Okay, so initial there is some SNR is there. I want to improve my SNR. Okay, so what do I need? All right, what do I need here is, let's say my noise factor input and output is, what is ideal is whatever is input is there, same amount should come out. Okay, right? The device is there which does some processing, okay, to the signal, gives me some signal out. If the ratio of the signal in and out remains the same, fine, ideal. Okay, so which is usually impossible, because whatever device which we use will fiddle with the signal. It is going to reduce the SNR for sure. Okay, if the reduction in the SNR is something like, if it is half, it becomes half of the actual signal. Okay, right, it's typical good amplification. Okay, if it reduces to, let's say, 10 times, okay, in that case, whatever design you made in the system is a very poor. Okay, right? So when it comes to quantum processors, your classical information is fed onto the quantum system. While feeding in, you figure out what is the SNR value, and you will feed it, and you, some processing is done, you get it out as an SNR out signal, and that you compare with the input. It should go in hand with respect to ratios. If ratios are somehow like half, it has become fine. If it becomes much smaller than that, okay, 10 times smaller than actual input, okay, that is a poor design when it comes to quantum circuit, what you design for a processing. Okay, fine. Again here, just like we did for SNR in decibels, you can also represent the noise figure in decibels. Same thought, 10 into log 10 of the actual noise figure ratio, SNR ratio. From there you can get, right? You can represent enough noise figure in decibels is 1 is ideal, 2 is reasonable, typically good amplification system it is, which amplifies in the classical communication. When it comes to quantum circuits which does the processing, so they are reasonably fine. If the circuit disturbs the input signal to so extent you get something noisy, there you should worry. Okay, right. So one of the take home in the last session I was telling is, in quantum there is nothing like one ideal amplification where only the signal gets amplified. Okay, right? I need to go a sequence of amplification methods. It's like a cascaded amplifiers. Okay, the first one does something, second one does something, third one does something. Very, very important to have this. And most important part is, first one should have a very good noise factor. Okay, right? And so, and first one should have a very good gain. Input signal to output signal should be enhanced when it comes to amplifier. So if the first one has a very good amplification, G1 gain, then it will be taken care. It will be used like to like add up to the later amplifiers. How? Through some formula is called a Frisch formula. You see here, first you have a noise factor F1, second noise factor which is subtracted by 1 divided by G1. If the G1 is very good, the correction factors become so small later on. Okay, how large G1 is, that much small correction factors will have. In that way, we can have amplification up to a very good level. So that is what design usually, okay, in the cascaded amplifiers. The first amplifier dominates the total noise figure. Okay, right? So high G1 is critical. Make the first stage gain large to suppress noise from downstream components. The later ones can be noise level controlled by the first one's gain. Okay, how it's very simple. You get a large gain. Later on, some noise factors are there, small noise factors. those things can be negligible compared to the large gain at the initial stage itself. So you anticipate some noise can come in later stage. That way, by anticipating it, you'll have a large gain in the initial stage itself. Okay, so that is the main motivation behind this designing this formula. Okay, fine. Now, okay, so we will can take a quick 5 minutes break here before going into the dynamical range. Okay, and if there is any questions, you can put it up on the chart here. So let's take a 5 minutes quick break, and we will come back at 4:20. Yeah, welcome back everyone. Yes, so there are small questions here. Uh, I hope you can see me. Uh, if you don't, I think I'll shift. Looks like there is some problem. Wait a minute. Hello. Yeah. Okay. There's a recoil somewhere. Just a minute. Hello. Yeah. I hope people can hear me and see me. Yeah. Yeah. Okay. Okay. So there were some questions here. Okay, regarding this part. Yeah. So what was asked is, just a minute, just scrolling through the chart. Okay. Okay, my network is seriously slow. Uh, okay, so there is a question here by Bala Yoga ji, Narendra ji. Is there a possibility for generating a latch with feedback in Cascade, and any papers on that clock generation in Cascade? Okay, it's a very valid question, Narendra ji. Uh, like whatever we do in electronics and conventional communication may not be straight away applicable in the case of quantum. Okay, right? Please remember, one good thing in quantum is feedback is not required. Okay, right? I can always have two inputs, two outputs for any given quantum circuit, right? Or at least single qubits, one input, one output. Two qubit system, two inputs, two outputs. Okay. So why do I need feedback in the case of classical communication? Just to put my output under the requirement, under the control. I'll keep the feedback from output to input so that the one extra channel is there, that feedback channel is there, I'll have a control. But such a thing will not be required in quantum computing because it comes by default to multiple inputs and multiple outputs in the quantum gates as such. So I may not be exactly able to give a straight away answer for your question of commenting on possibility for generating a latch with a feedback. Okay, right? But you can work on it having a quantum advantage of multiple input and multiple output, and also very important part of it is called the reversibility. Means I can always get back my input from the output. Okay, fine. So that is one question. So another question is, let me. Okay, so it is so much blurred. Huh? Okay, let me take my video. Audio options. It should change. Yeah, it has come. Oh, right. Now that is one of the question. Uh, yeah, those who cannot see my screen, please refresh. You should be able to see. Okay. All right. What is the next question? Okay, here. Uh, Can you explain the terms involved in Frisch formula? Yeah, you see G1, G1, G2 are the gains. Let's say I have not just one set of amplifier to amplify my signal when it comes to quantum circuit. I have multiple amplifiers, let's say classical versions and quantum workflows and all. It is a bunch of amplifiers. Each is meant to amplify certain part of the signal. Okay, so in that way, the first one is supposed to have a very high value of gain. So the G1s, G2s are gains. F1, F2, F3 are actually noise factors. NF I wrote earlier. Okay. So instead of writing NF, I just wrote F. They are the noise factors. So what is the noise factor? NF is SNR in to SNR out. They're meant to be equal in SNRs. So NF's meant to be 1. If it is half of it, okay, then fine, reasonable. But it cannot be much smaller than half. If it becomes 110, then it is seriously problematic. Okay. F, F1 would be a noise factor from the first amplifier, and F2 would be noise factor from the second, and so on. So those all things put together is going to give me Frisch formula F factor. Okay, right? So having a large G1 would get rid of the later corrections. Okay, I'm not be needing additional amplifiers. The first one is doing such a correction. That is what it is conveying. Okay, right. Okay, next. Okay, please see the screen is not visible. In that case, please check it. Okay. Mm, yeah, Lakshmanan is asking one basic question. So far, we have talked about noise in decibels, and at one place we started expressing the noise in half a photon. Can you please explain the correlation? So correlation. Very good. Okay. Please see conventional information processing, signal processing, we talk in terms of SNR, which is the ratio of power in, power out. I hope I am right. Sorry, not power in, it is power signal, power of noise. Okay, the noise is seriously high, okay, which is going to spoil my SNR. Okay, SNR is usually meant to have very large values. How large? Is about 10 to the power of 3 is a very good. 10 to the power of 2 is reasonable. Okay. 10 is problematic. Okay. Why? Because the signal is disappearing in the noise if I have very, very small SNR values. Okay. We saw that example last time. So instead of giving such a large number to specify SNR, what people do, they specify such large number in terms of decibels. How? You take SNR in decibel by take 10 multiplying into log of that conventional SNR in the base of 10. So here what happens? 10 into log 10, 10 cube. So which is going to be simply 30 dBs. So instead of writing 10 to the power of 3, SNR ratio, you just say 30 decibels. Okay, fine. This is a conventional way of representing what is a noise in the system. 30 decibels is reasonably fine. Okay, signal SNR is fine means the noise is just only 1 out of 1000 parts. Okay, that is what 30 decibel mean. Now, when it comes to quantum systems, this is a conventional classical information processing, signal processing. Okay, in the quantum case, I was telling you last time, let me put it back once again. Let's say I have a one-dimensional box. Okay, means if I put something inside, that can only go back and forth one dimension. So what I'll do, I'll put one electron in this box. So I have created a potential for this electron to only go left and right. What do I do? I'll put a Wahl's infinite potential on the other side. Okay, so the electron can only go left and right. Okay, it cannot go up. Please remember that it's a one-dimensional box. So left and right electron can go. Let's say box size is 0 to L. Okay, the position is spread between 0 to L. This is a one-dimensional box for you. If I put an electron inside, it's so small. What happens? It's so small because of this tiny nature. Okay, de Broglie said it can move around due to its internal energy, which comes because of vacuum fluctuations, it is called. So let's say it's a fancy for us, we don't understand vacuum fluctuation. What do? I'll try to study the dynamics of this electron in such potential. Okay, right? What is a potential? Just like you take a small bowl, you put a marble in that bowl, you leave the marble, it makes an oscillation. So this is a parabolic potential. In the parabolic potential, if you leave a marble, it's a classical system or a macroscopic system, macroscopic. Okay, where marble is making oscillations, just like a pendulum making oscillations. Okay, likewise, analog. If I take an electron, put it inside a potential well like this, in fact, it makes a dynamics. It shows some dynamics. I don't know what kind of dynamics it is. I want to understand that. For that, what should I do? I need to use some kind of equations of motion. Some kind of see here, I have F is equal to ma, Newton's second law, which can be used to find out what is the dynamics of the system. And here, I can't straight away use that Newton's equation. Newton's second law I can't use. Here I have to use Schrodinger equation. What is the Schrodinger equation? It is just like Newton's second law, but at microscopic level. What you should do? You should use Hamiltonian of the system, which is going to have kinetic energy of the system plus potential energy of the system expressed in terms of quantum observables. Observables in the sense, it's like a measuring tools. Position observable, momentum observable. Likewise, that's where I put a hat. So Hamiltonian is some kind of a energy observable. It measures the energy. It's like a thermometer measures the temperature of a patient. The same way, H Hamiltonian will measure the energy of the system. It is not the energy, but it measures the energy. So here, kinetic energy is represented as P square by 2m, where momentum is P with a hat, plus potential is some potential U of x. Okay, what potential it is? The potential U of x is here is infinity for x less than 0 and infinity for x less than greater than L. Okay, 1 minute. And it is equal to 0 for x between 0 to L. So that is the potential I have here. So for such potential, what is the dynamics of the system? Now I take H. Let's say a system exists in some quantum state psi, and I can find what is with energy with which this system can exist. So this is the eigenvalue equation. They call, in fact, it is equivalent to Schrodinger equation. How? I represent H using these two things. I'll put it back and I'll solve this for a given energy, for required energy and the quantum state. Okay. Now I have used in Dirac notation. We can use in regular notation. Here, psi of x is in expression form, some kind of a wave function. Okay. Here, see, for a dynamical system, I need a derivative to find the dynamics. See, for example, in Newton's law, acceleration is second order derivative. You say, so there the second order derivative is there. Where is the derivative here? Yes, derivative can come in two ways. In terms of position, momentum also it can come. Let's say momentum along the x is minus ih cross dou by 2x, position derivative, and also time derivative also can be ih cross dou by dou t. So in this way, I can convert my eigenvalue equation as per my required study. Let's say I want to study the system in position, I use this kind of a derivative. If I want to study the system in time, I use this kind of a derivative. When E becomes a derivative, H remains as it is. Okay, H will become some kind of a number or some kind of a matrix. Okay, if H is expressed in terms of momentum and potential energy, in that case E remains to be energy, a value. Okay, now let's say I use the momentum derivative and solve this differential equation for some solutions. What solutions? For a given this potential energy, if I solve this, you know what happens? I'm going to get some solutions. Let's say I'll get some psi1 of x which exists with energy E1. Psi2 of x exists with energy E2. Likewise, so many energies, so many quantum states are going to exist. If I plot these quantum states with respect to position, you know what happens? Okay. What happens is, for n equal to 0 means ground state, I'll have a system something like this. Means half a wavelength of the wave is confined. If we write a standing wave pattern or something like this. Okay, corresponding quantum state is psi1 of x. And the next one is something like this. Standing wave pattern is something like this. So this is E1 psi2 of x. Okay, so many such states exist for a given n value. Here n is equal to 0, ground state, n equal to 1. So where these n's are coming, because if you solve these differential equations are going to have multiple applicable solutions. Okay, what kind of multiple solutions? They are integer multiple solutions. So where n is that integer, n stands for 0 means ground state energy of the electron, n is equal to 1 excited state energy of the electron. Now you see, overall the energy of the system, if I have to write down, energy is for a nth orbit, a nth quantum state is equal to Okay, n plus half into h omega. This is the overall energy of the system for any given nth state. Okay, in the nth state, this is the energy. But if I substitute n equal to 0, and what happens? E of 0 is h omega by 2, which means even in the ground state of the system, I have fluctuations. What kind of fluctuations? Electron can vibrate or create a wave which has a wave disturbance, something like this. Okay, right? Means there is no way you can put the ground state of the energy of the system in such a way there is no disturbance in the system. That is impossible. So half a energy of a wavelength energy with angular frequency of omega photons would exist in the system even in the ground state. That's why it's called a vacuum state, or it called also 0 point energy state. Okay, it is impossible to have zero energy for n equal to 0 state. Okay, where is this expression is coming? This expression is coming when I solved the Schrodinger differential equation for a given potential well, this type of potential well. If I solve it, I'll get this. So here in this case, the noise is, I can't have a noise in the energy, okay, less than h omega by 2. So the noise is always more than h omega 2. Means even I reduce the temperature of this electron inside a box to absolute zero Kelvin, even in that case also, the system is going to have this much of energy. Okay, so I would say the if I start the system in ground state without no vibrations or without no oscillations, which would be absurd. So it is always more than that. From that point, you have to have the energy of the system. So it's like a error correction. So in quantum systems, if the incoming energy is something less than this disturbance, okay, half a photon, h omega by 2 value, then your signal will be lost in this noise. So the incoming energy must be much, much larger than this value. So incoming energy much larger than, so that the noise which is there may not disturb, may not create issues in the case of quantum readout mechanism, quantum processing mechanism. Okay, so that is the answer for your question. I hope you got that. Okay, right. So in the quantum case, it is represented in terms of what energy, what is the error in the system it has. Okay, right. Okay, so what is yeah. Okay, so F I had explained. Why should we call half h omega by 2 as a noise, sir? Because see, I meant the system to go to zero, no disturbance, no noise, or no vibrations, but it existing in the vibrations with the energies of h omega by 2 value. Where it is this coming? This is coming from this equation. Where is this is coming? This is coming from solving this eigenvalue equation. This is eigenvalue equation. If you solve this, you will get this value. Okay, right. So that's where we are calling h omega by 2. Okay, so let me scroll down. Any other question? How to sense a single quantum? Yeah, that is a very good question Abdul Karimji is asking. So the entire, like say, I would say 80% of the quantum research is about creating a single qubit and detecting a single qubit. Okay, so to detect something of a single qubit level, you need to have a detectors capable of creating single photons. Okay, so the entire technology-wise research is creating a single photon source, detecting single photons. So that is all about. So the people are, as of now, capable of creating single photons. Okay, not as simple as like say AK-47 gun continuously sending single bullets one after other. That kind of a single photons will not get. Okay, so a bunch of photons will be coming. So from there, we should have some kind of a mechanism where few photons can be picked in certain time bandwidth. Okay, so that is where the technology is going to play a very vital role. Okay, so the finally, when do we get energy is equal to n h, okay, for particle in a box case. Okay, very good, very good, very good. Okay, good. I think yeah, what you are asking is a question. Okay, for the case where potential, like a particle is in zero potential. Okay, so in that case, what we can say, right? X is equal to 0, x is equal to L. In this case, you know what happens? If at all, if the particle is inside a box, it cannot exist at x equal to 0. It cannot exist at x is equal to 1. Okay, potential is 0. U of x is 0 inside, right? It's 0 potential. Okay, so this is called potential well. Inside it is 0. So left and right is infinity. In order to go out, somebody has to supply this much of infinite energy to go outside to other side. So it is stuck inside this well. So in this case, you will have a dynamic differential equations. Okay, p square by 2m is simply minus h square by dou squared by dou x square. Okay, I will write in terms of position x only. We can solve it for y and z. Okay, this is what I have. Okay, so I'll have h psi is equal to e psi. Okay, so let's write down quantum state in some function of x, wave function. Okay, what do I have here? Minus s square by 2m dou square by dou x square psi of x is equal to e psi of x. Okay, right? So now let's write down the differential equation into much easier form, which is going to be dou square by dou x square plus 2me by h square multiplied by psi of square is equal to 0. This is the differential equation I have. Okay, so if you want, I can put in here like this also. I can write for your convenience. Okay, so let's say this is some factor. This is some factor. Okay, which is oh yeah, this is some I think it comes out to be some units of omega, I guess, omega square. So okay, rk, yeah, some factor. Okay, x square, which is equal to 0. This is a second order differential equation, linear differential equation. So this will going to have, I'm sorry, it's not omega, it has to be k, I think, k square. Yeah. Okay. So this will have a solutions which is sinusoidal solutions with some amplitude sine of kx. Okay. Right? If you take and substitute here, you will get this. This is going to satisfy. Okay. So what is this telling? It is a sinusoidal function which satisfies this differential equation, which means my particle, if I keep it inside such a zero potential, it is going to create a wave disturbance inside. So that wave is going to have a propagation vector k value. What is the propagation vector k? This is going to be square root of 2me by h square. That is a propagation vector for a sinusoidal wave. Okay. Now, okay, you see here, this differential equation should have a solution which should vanish at x is equal to 0, which should vanish at x is equal to L. Okay, why it should vanish? The particle should not be found there. There should be a node there. Okay, the wave should have a node. This is the anti-node, and node, node here, and node here. means electron should not be found at the node. Okay, so x is equal to 0, straightforward. Sign of 0 is 0. But what about x is equal to L? When I have x is equal to L, what happens? This becomes sine of KL. So when this can go as 0, whenever sine KL is equal to 0. When sine can go to 0, which is KL is equal to n pi. Okay, right? Which implies what is a which implies k is n pi by L. So how many such k's can exist? N is integer. Many n's can satisfy such propagation vectors. Means I can have a wave. Okay, this kind of a wave. I can have this kind of a wave. I can have a wave like this also. So in that way, I am going to get many propagation vectors which are functions of n, which implies, okay. So what is a k, by the way? K, I just we have, this is a k. So k has a dependence on integer n. Okay. So let me substitute k, n is equal to n pi by L, which is square root of 2me by h square. Here you see, on the left hand side I have n, on the right hand side I have energy. So mass is fixed, h is fixed. So E is going to dependent on n. So which means I'll say n. So what is the energy? Energy is n square pi square L square. Okay, 2m, on the numerator I have h square. So this is the energy of the system in the nth orbit. Okay, so exact value in terms of Planck's constant, mass of the particle, and in which wave box it is confined, that is given here. Okay, right? So when n equal to 0, this will say energy of the system is 0, straightforward. Okay, so what is this calculating is, this is calculating above the 0 fluctuations. Okay, so you should remember the 0 fluctuation is there by default, above which energy would exist. Okay, so what did you ask is a very, very valid, important question one should know, right? So this value is calculated above that h omega by 2. Okay, right? So fine, I will have other questions. So we have yeah, Prahaladji asking dynamic range. I don't understand what is a dynamic range. Okay, so maybe you meant the dynamics of the system. Okay, so dynamic range, the system can have many such dynamical ranges. Okay, right. So earlier, thank you, Sudeep ji, asking why we took energy is equal to n plus half h bar omega. Okay, so this is a different potential. Okay, so in the different potential case, we solve the, see, here I solved the system in a way, it's called semi-classical way solving. If I confine the system completely quantum, so in that case, I will get this pure quantized system where the particles are meant to exist in nth state. Okay, so this is a quantum mechanics for you, quantum physics for you. If you start going in depth, you will appreciate that. For time being, you please consider as of now. This is a energy of the system which I get by solving eigenvalue problem of the Hamiltonian of the system. Okay, fine. So we need to quickly complete our presentation. Okay, right. Where we start. Okay, this we continue. Yeah, nice figures. This we discussed. Dynamic range. Yes. Okay. Okay, you meant the dynamic range of the PPT. Ah, okay, I'm sorry. Okay, so dynamic range here is just like a ratio. We had several ratios, quantifying ratios for the signal. Okay, signal quality. Okay, right. So the signal is going to vary through the circuit, let's say in the quantum circuit, right? So it can reach some maximum value, it can reach some minimum value. Okay, there are desired range. I should not have too much low power as going through the circuit, or it should not have too much high. So there should be a power max I should have and power min I should have, certain desired value. So that is actually a quantifying factor is called dynamic range. Now, what is desirable? You can see here, for example, lower limit. Okay, so where the noise is there, okay, and below this signal is buried inside the noise. So that is a bad. Okay, so here dynamic range, the noise is this noise floor, right? Your high power is somewhere here, and the low power p power is here. Okay, so if the system, the signal is fluctuating, okay, so in this case dB, if you calculate, right, so you would get certain dB dynamic range. So the upper limit is saturation, which can amplify, and output distorts. Okay, and too much operating window. Okay, so too much is not good. This is upper limit dB range. This is a very low range where the noise is like inside the noise signal is this disappeared. Okay, so operating window you choose only signals with dynamic range are faithfully processed. Okay, so you usually choose certain range within which you will have a very good information processing, signal processing. Okay, so you should not fall at the top, also you should not fall at the bottom. Okay, so that is what dynamic range quantifies your signal conditioning, which is required for us to understand the quantum information processing. Okay, right? This is just simple ratio, by the way. Power max to power minimum in the system, how much power max it can take, okay, or how much power max it can have. Okay, so I have a regular example which is taken from one of the source, which is put as a reference at the end. Here you see, okay. So ideally, what is there? Ideal output, actual output is this, and dynamic range where we can work on. This is the dynamic range in terms of power out, power in. Okay, right? So we usually anticipate as we increase the power, the output would go on. It is not. It gets saturates. Okay, so you should not go on to work after saturation. So you should limit yourself within this range where we have a very good relation to input to output, linear relation. Okay, right. Fine. The next question is noise temperature. So how the noise is going to affect, sorry, how temperature is going to affect, how it can be represented in terms of straight away noise factor itself. Okay, so you can say there is a power involved in the noise. Noise comes with its own power. Okay, so earlier we had a P noise is equal to T into a Boltzmann constant multiplied by bandwidth. So I just represent the noise in terms of temperature here. So why do I need? This will help me to straight away quantify the noise in terms of temperature. Okay. So the moment if I do that, I can relate that to noise figure. So noise figure is 1 plus a specific temperature Tm some particular, and we'll just compare with the zero temperature, which is a 290 Kelvin. Okay, let's say 0 degrees Celsius. At that point, we'll refer as a base or a reference point. From there, we measure what is the noise in terms of temperature. This is a specific temperature meant to give a certain noise, right? So we'll not measure that noise in terms of any power or anything. We'll measure in terms of actual temperature itself. Okay. So here noise figure versus system temperature, just a comparison histograms we have given. Okay. Where in the case of quantum computing, which is done at a millikelvin cryogenic temperature, so there what is a noise figure is given. If a dilution refrigerator, if I use a helium-3 fridge, again cryogenic, and helium-4 crested, I'll have what kind of a noise figures I have. If I increase to a little higher temperature, so noise figures are going to increase. In room temperature, you see a noise figure is much higher. Okay, right? Basically quantifying the noise in terms of temperature. Okay. Again, coming back to our standard quantum limit, you cannot reduce the oscillation vibrations in the system whose energy cannot be less than h omega 2. Okay, which is going to be added noise in the system, because the system comes with such initial value of vibrations or the noise or the disturbance. Okay, right? So let's say I have two quadratures like a position and momentum. Let's say I have two quadratures, x1 and x2, right? So position in the x and position in the y axis. In that case, you can have the errors greater than h cut by 1 by 4. This relation also can be shown is similar to delta x delta p having more than h by 2. Okay, right? Okay, standard quantum limit we already discussed. I think I showed you how we need to compress one of the quadrature to have a good control in that particular case. So this is called squeeze state, you see, and the vacuum state is something no disturbance except vacuum disturbance, which is about h omega 2. So this is a vacuum state. Okay, beyond which if the noise increases, you will have a standard quantum limit, and I squeeze it to reduce one of the quadrature error and have a squeeze state. Okay, right? This is another way of seeing things. Okay, yeah. Okay, so quantum measurement chain, the applications, qubit and resonators I use. Okay, so that is for the readout mechanism. Somebody was asking, how do I read it? So there are resonators, which like some kind of a sync mechanism, go near the qubits and extract that information. Okay, and this is the amplifiers we use, HEMT amplifiers that we saw last time, and cryogenic amplifiers we use, and electronics, conventional electronics were used to retrieve the signal. Okay, so this is all the overall quantum measurement chain would have. So each one comes with its own SMA, SNM, SNR, dynamic range, and noise figure, and noise represented in terms of temperature. All those factors are there. In that way, we'll study the system. Okay, key takeaways. SNR is a fundamental metric. Noise figure is quantifies a degradation of the system. Cryogenic cooling is very much essential. Amplification always adds noise. And dynamic range sets the limit where we can work with the system. And SQL, standard quantum limit, is something fundamental. We can't get away with that. There is a boundary within which we have to work. Okay, so that's about overall signal conditioning and noise mitigation of my both the sessions last time and today's session. So let me end it here by saying in classical systems we fight the noise, in quantum system we respect it because it is there by default. And noise is not a limitation of the technology when it comes to quantum computing. It's a property of the nature. We should learn how to work around it. Okay. So thank you very much for listening. And these are the references like I told you earlier. And if there is any more questions, I can take. Okay.
Thank you very much, sir, for your valuable time. If there are any questions, dear participants, you can just ask. We have already gone beyond your time, but in case, I think most of the questions have been answered. Yeah, participants, kindly note the quiz exam will be is open, almost open now. You can take the quiz if you are ready. Otherwise, you can take it till Saturday afternoon, 12 o'clock. You have to complete before you come to the quiz. You complete so that by the end of the schedule, we will give you the certificates. That's what we are targeting. For those who are not able to do it, we will keep it open. You can but 12 o'clock we will close the this thing for some time so that we will take the result of the quiz and then open the other aspects for others to take the quiz. But the certificates will be issued later, right? So for those who have shortage of attendance, the list will also be put up tomorrow, and then you can check up whether the attendance will be calculated till tomorrow evening's lecture. Okay. So tomorrow evening we'll take out the attendance and put up on the list. So you'll have to submit a retaking form by Monday that you have watched the respective videos, at least few videos you have watched. And once you submit the undertaking, we will release the certificates if you have finished all the 3 quizzes. Taking all the 3 quizzes are important. So please ensure that you will attempt all the 3 quizzes. Depends on the marks, you will get the grades, whether it is excellent or very good or good or satisfactory. Please try to complete the quizzes. So hopefully you will try to do it Sunday afternoon. Sir, certificates will be released on Monday if we make it to Sunday afternoon. We will open it again in the evening after the lecture is over at 5:30. We'll open the quiz. You can complete the exams. We will release in the next cycle. We will release it on let us say Monday or Tuesday, whatever be the time, right? So accordingly, on that day we will issue the certificates. Next course is starting next Friday. That is QT10, QT10, sorry, QT10. So please be ready because it starts on 8th, na? Dipesh ji, 8th, I think, right? May 8th. Friday it will start. So it is going to be May 8th. Naveen? Yeah, May 8th it will start. Friday and Saturday, 2 lectures will be there, and then we continue. So please, those who are interested, it is on solid state physics. You will again meet Dr. Ashwath Babu in the course in solid state physics, right? And then quantum optics starts in the month of June, right? Thank you so much. We will meet tomorrow at 2 o'clock. Please note, lecture is from 2 o'clock, 2 to 4, Janani ma'am, 4 to 6, Mustafizur Rahman, right? So please share the flyer. Yes, we will put the flyer in the group. Devlina madam, you are in the WhatsApp group. So we will put it in the group. We'll put the link also in the group. Naveen or Dipesh or Diksha. Diksha, are you there? Okay. Diksha, you can put the group in the group. You can post these things. So quantum optics more. Yes, yes, sure, no problem. The both the brochures will be posted in the group. Okay, so you can register for that, right? Yeah. Thank you so much. Yeah, we will
Yeah, I
meet
have shared.
tomorrow. Yes,
Yes,
sir.
sir. I have shared my both the PPTs and
Okay, sir.
this my Blackboard part also I have shared in
Right,
the
sir.
Canva itself. People can check for the exam if they need.
Right, sir.
Uh, yeah. Okay.
Right.
Good luck.
Actually, Ashwath sir directly puts the questions and material directly
Thank you.
in the canvas. He helps us. So that way. So please, the material is ready till today afternoon. All the material is laid. I think we may not have questions on L. Venkat Subramaniam sir's session because it was more of an industry presentation. So the slides I will share once Dr. Venkat Subramaniam gives it to me, right? So tomorrow, 2 o'clock, tomorrow is holiday, but kindly spare these 4 hours, very important. 2 hours on related to quantum cryptography and 2 hours related to this topic is digital communication, which he will do. Now they will change from complexity to digital communication. He'll do that, right? Thank you so much for joining. We'll take a break. Thank you, Ashwat Babu sir. Thank you
Thank
for
you, Puneet.
joining.
Yeah.